Check, check. Checking, checking. Hello, hello, check. Soon we see. So, हिजो यहाँ चाहिँ पढाएको जस्तो लाग्यो च्याप्टर 3 सुरु गर्नु पऱ्यो आज. Understanding tensor, the basic data structure in PyTorch, indexing and operating on tensors, interpreting, interoperating within NumPy dimensional arrays, moving computation to the GPU for speed. In the previous chapter, we took a tour of some of the many applications that deep learning enables. They invariably consist of taking data in some form like images or text, and producing data in another form, like labels, numbers, or number images or text. Viewed from this angle, deep learning really consists of building a system that can transform data from one representation to another. This transformation is driven by extracting commonalities from a series of examples that demonstrate the desired map. For example, the system might not know the general shape of a dog and the typical color of a golden retriever. By combining the two image properties, the system can correctly map images with a given shape and color to the golden retriever label, instead of a black lab or a tawny tomcat. For this matter, the resulting system can consume broad swaths of similar inputs and produce meaningful outputs for these inputs. The process begins by converting our input into floating point number. We will cover converting image pixels to numbers as we see in the first step of figure 3.1 in chapter 4, along with many other types of data. But before we can get to that, in this chapter, we learn how to deal with all the floating points number in PyTorch by using tensor. Okay, the old as floating the old as floating number point numbers. Since floating point numbers are the way a network deals with information, we need a way to encode real world data of the kind we want to process into something digestible by the network and decode the output back to something we can understand and use for our purpose. So इमेजलाई चाहिँ इनपुट रिप्रेजेन्टेसन भ्यालु अफ पिक्सललाई चाहिँ नम्बरमा लगायो नि नम्बरबाट नेटवर्कमा पास गर्ने नेटवर्कबाट आउने आउटपुटलाई चाहिँ लेभलमा म्याच गर्ने हो क्या. Similar inputs should lead to closer representation, especially at deeper levels. Okay. Or deep neural network typically learns the transformation from one form of data to another in stages, which means the particular transform data between each stages can be thought of as a sequence of intermediate representation. For image recognition, early representation can be things such as edge detection or certain texture. Like for deeper representation can capture more complex structure like ears, nose, or eyes. In general, such intermediate representation are collection of floating points, number that categorize the input and the capture the data structure in a way that is instrumental for describing how inputs are mapped to the outputs of the neural networks. Such characterization is specific to the tags at hand and is learned from relevant examples. This collection of floating point number and their manipulation are at the heart of modern AI. We will see several examples of this throughout the books. It's important to keep in mind that the intermediate representation like this shown in the second step of figure 3.1 are the result of combining the input with the weight of the previous layer of neurons. Each intermediate representation is unique to the inputs that processed it. Before we can begin the process of converting our data to floating point input, we must first have a solid understanding of how PyTorch handles and store data as input, as intermediate representation and output. This chapter will be devoted to precisely that. To this end, PyTorch introduced a fundamental data structure, the tensor. We already bumped into tensor in chapter 2 when we ran inference on pretend network. For those who came from mathematics, physics, or engineering, the term tensor come bundled with the notion of space, reference system, and transformation between them. For better or worse, these notions do not apply here in the context of deep learning. Tensor refer to the generalization of vector and matrix to an arbitrary number of dimensions. As we can see in dimension in figure 3.2, another name for the same concept is multidimensional array. The dimensionality of a tensor is coincide with the number of indices used to refer to scalar values within the tensor. So scalar is zero dimensional, vector is one dimensional, matrix is two dimensional, tensor is three dimensional, and multi-dimensional tensor. Okay, PyTorch is not the only library that deals with multi-dimensional array. NumPy is by far the most popular multi-dimensional array library, to the point that it is now arguably become the lingua franca of data science. PyTorch features seamless interoperability with NumPy, which brings it to first-class integration with the rest of the scientific libraries in Python, such as SciPy, scikit-learn, and pandas. Compared to NumPy arrays, PyTorch tensor have a few superpowers such as the ability to perform very fast operation on graphical processing unit, distribute operation on multiple device or machine, and keep a record of the graph of a competition that created them. These are all important features when implementing a modern deep learning library. We will start this chapter by introducing PyTorch tensor, covering the basic in order to set things in motion for our work in the rest of the book. First and the foremost, we will learn how to manipulate tensor using the PyTorch tensor library. This includes things like how the data is stored in memory, how certain operation can be performed on arbitrarily large tensor in constant time, and the aforementioned NumPy interoperability and GPU acceleration. Understanding the capability and API of tensor is important if they are to become go-to tools in our programming toolbox. In the next chapter, we will put this knowledge to good use and learn how to represent several different kind of data in a way that enables learning with neural networks. So tensor multidimensional array. We have already learned that tensor are the fundamental data structure in PyTorch. Or tensor is an array that is a data structure that stores a collection of numbers that are accessible individually using an index and can be indexed with multiple indices from Python list to PyTorch tensor. Let's see indexing in action so that we can compare it to tensor indexing. Take a list of 3 numbers in Python. Google Colab मा गरिहाल्दै हेर्नु पर्यो. So 3टा बनाएको छ 0 एक्स्ट्रा के गरे जस्तो छ हैन. यति पनि गर्तिर आउन 0 1.0 2.0 1.0. It is not useful for simple Python program dealing with vectors of numbers such as the coordinates of a 2D line. To use Python list to store the vectors, as we will see in the following chapter, using a more efficient tensor data structure. Many types of data from image to time series and even sentences can be represented by defining operation over tensors, some of which we will explore in this chapter. We can slice and manipulate data expressly and efficiently at the same time, even from a high level and not particularly large language such as Python. Constructing our first tensor. Let's instruct PyTorch tensor. Import बनाउने हो त्यसो पछाडि ons बनाउने हो. E is equal to torch.ons on. त्यस पछाडि कतिवटा 3 1.0. Tensor 1. Name tensor is not defined. Mathi tensor. What? Okay. Float signal दिन्छ र is. Error there. After importing the torch module, we call a function that creates a one-dimensional tensor of size 3 filled with the values 1. We can access the element using zero-based index or assign a new value to it. Okay, so the presence of tensor. The Python list of the tuples of are collection of Python objects that are individually allocated in memory as shown on the left in figure 3.3. Torch PyTorch tensor or NumPy arrays on the other hand are views over typically contiguous memory blocks containing unboxed C numeric types rather than Python objects. Each element is a 32-bit for type float in this case, as we can see on the right side of the figure 3.3. This means storing a one-dimensional tensor of one. Okay, 1000 lakh 10 lakh 10 lakh. Okay, 10 lakh float number will require exactly 40 lakh per digit bytes plus one over for material such as dimension and numeric type. Say we have a list of coordinates we like to use to represent a geometrical objects, perhaps a 2D triangle with vertices at coordinates 4, 1, 5, 3 and 2, 1. The example is in a particularly pertinent to deploying, but it is easy to follow. Instead of having coordinate as number as in a Python list as we did earlier, we can use a one-dimensional tensor by storing x in even indices and y in the odd indices. So Python list बनाउने memory tensor array. So point 0 to tensor 0 को 6 बनाउने त्यसमा 6 वटामा लेख्नु नि. Okay. सन्ध्या हुन्छ यसरी पनि पोइन्ट्स बनाउन सकिन्छ भने देखाएको यसलाई. पाँचवटा म्याट्रिक्स भन्यो यसको साइज कतिको बनायो त 3 को भनेपछि 3 डाइमेन्सनको भनेपछि 1 1 1 3 2 सेप हेरौँ एकचोटि पोइन्ट्स 1 3 2 डबल ब्राकेट राखेर मैले डबल ब्राकेट राखेको छु होइन 3 3 2 को बनाइरहेको रहेछ सेप ओके the output is another tensor that presents different values. The new tensor is a 1D tensor of size 2 into the referencing the values of the first row in the point tensor. Thus, this means a new chunk of memory was allocated, values were copied into it, and the new memory was returned trapped in a new tensor object. No, because that would be very insufficient. Especially if we had number of points, million of points. We'll revisit how tensor are stored later in this chapter when we cover views of tensor in section 3.7. Indexing tensor. What if we need to obtain a tensor containing all points but the first? Let's easy using range index notation which applies to standard Python list. Here is a reminder. लिस्ट रेंज राखेर निकाल्नु खोजेको र 4 सम्म तर दुई स्टेपले बढ्ने भने हो र 1 2 So from element 1 inclusive to for step of 2 okay to bana ho ja to achieve our goal we can use the some same notation for PyTorch tensor the with the added benefit that just in NumPy and other Python scientific libraries we can use range indexing from each of the tensor dimension. Three by two matrix. After the first one. ओके फर्स्ट कलम लिँदो रहेछ तर फर्स्ट रोलाई छोडेर अर्को कलम ल्याउने भने ओके यो पोइन्ट्स 1 को देखायो तलपट्टिको सबै भनेको रहेछ ओके 0 पहिला कोलममा जान्छ होइन पहिलो कोलम लेन्थ 0 होइन 1 बाट अच्छा अच्छा Using ranges, PyTorch features a powerful form of indexing called advanced indexing, which we will look at in the next chapter. Remember encoding and dimension and write our indexing accordingly. As data is transformed through multiple tensors, keeping track of which dimension contains the data can be error prone. Okay, error prone हुन्छ भन्छ त भयो To make things concrete, imagine that we have a 3D tensor like image T from section 2.4 2.1.4. We will use dummy data for simplicity here, and we want to convert it to a gray scale. Okay, we look up typical weights for the colors to derive a single brightness values. मान्छे एउटा इमेज बनाउनु चाहिँ ट्राई गरेको छ ओके imgt is equal to torch.tensor त्यसमा चाहिँ 3 को 5 को 5 weights we also often want our code to generalize. For example, from grayscale image having this represented as 2D tensor with height and with dimension to color images, adding a third channel dimension as in RGB, or from a single image to a batch of images. In section 2.1.4, we introduce additional batch dimension in batch T. Here we pretend to have a batch of 2. Okay. And then weight is equal to torch.tensor or torch.tensor. टेन्सरमा त 1 पोजिसन दिनुपर्छ कि खाली बिर्सिन्छ कि ब्राकेट दिनु This is a batch T. Okay. यो निकाल्ने तपाईँ -3 किन पास गर्यो थर्ड डाइमेन्सन -3 किन पास गर्यो टाइप पास गर्न मिल्दो रहेछ इनपुट पास गर्न मिल्छ इनपुट त अगाडि नै भइहाल्यो यो -3 किन पास गर्यो but we can generalize by counting from the end there are always in dimension -3 the third from the end the lazy unweighted mean can thus be written as okay त्यसपछि mean third no -3 but we can generalize by counting from the end there are always in dimension -3 okay the third from the end the crazy unweighted means can use be written as follows okay batch great 5 by 5 को भएछ ग्रेन नेम अनि टर्च साइज यो चाहिँ 2,5 by 5 को भएछ ए -3 को लागि मिन गर्दै गरेको त हटाइदिएको हो अनि स्विच गरे जस्तो पो गरेर रहेछ त ओके त्यो त इमेजको साइड लगाएर It also appends leading dimension of size automatically. This is called broadcasting. Okay, broadcasting batch t of size 2355 is multiplied by one squeeze weight of shape 3 times 1 by 1 resulting out tensor of size. मल्टिप्लाई गर्दाखेरि के हुन्छ र भन्दाखेरि 311 को भयो भने पनि 2355 हुन्छ, from which we can then solve the third dimension from the in. So on squeeze weight on SQ SQUEC on squeezed weight. लास्टलाई पो निकाल्दैन नि, दुईटा फाल्ने त्यसले त। भनेपछि ब्याच वेटको सेप भनेको 2/5/3 ब्याच वेटलाई त हामीले के गरेको, ब्याच वेटमा ब्याच वेट इन्टु अनस्क्विज वेट गरेको थियौँ होइन। ओके, सो यो अनस्क्विज वेटको सेप चाहिँ कति 311 भनेको आई थिङ्क पहिला वेट्सको साइज कति थियो, वेटको साइज त भनेको चाहिँ 3 डाइमेन्सनल थियो यसको त वेट्सको साइज त 3 डाइमेन्सनल थियो त सेप। सो यो त 1D मा 3 थियो होइन। सिधै यसलाई के भने एउटा चाहिँ स्क्विज भनेर हटाउने होइन, अनस्क्विज भनेर एउटा पो थपे रहेछ भने चाहिँ पहिला एउटा थपे लास्टमा, फेरि अर्को थपे है 311 को बन्यो। ओके, अनस्क्विज वेटको साइज 311 को। ओके, त्यसरी इमेज वेटमा इमेजको टी भनेको 355 को थियो, त्यसलाई अनस्क्विज वेटमा मल्टिप्लाई गर्दैछ कति भयो, स्क्विज गर्दैछ 35 अनस्क्विज होइन। आई थिङ्क वेट इमेज वेट भनेको 355 हुन्छ, 355 इन्टु 311 भयो भने 355 हुन्छ नि। ओके, त इमेज चाहिँ 355 को छ होइन त। सो ब्याच वेट भनेको कतिको छ, ब्याच वेट टी सो 2355 को थियो इन्टु अनस्क्विज वेट्सले गरिदियो नि त 355 भने 2311 को भयो 5 2311 को 11 इन्टु 55 भने 2355 हुन्छ। ओके, त्यसो चाहिँ इमेज ग्रे वेट भनेको इमेज वेट्सको साइज कति छ, इमेज टी भनेको इमेज टी 355 इन्टु 311 355 इन्टु तर माइनस सम गर भने -3 क्या लाई चाहिँ सम 0 गर्दै भनेको छ किन भाइ इमेज so emg gray weighted यसलाई पिन्दैन न त के आउँदो रहेछ यसको सेप 5/5 को इमेज 5/5 को कसरी आयो भने सम -3 गरिदिनु भनेको चाहिँ हटाइदिने हो समले -3 गर्दा हट्छ साइज सम -3 गर्दा के हुन्छ भने 0 1 2 3 यदि इमेज वेट प्रिन्ट हालेर छोड्नु भनेको That's it. Okay, 355 को थियो 355 को थियो तर सम -3 गर्दाखेरि 5/5 को कसरी हुन्छ यो के हो यो यस्तो सम I think answer that sum -3 भने के हुन्छ माइनस यदि माइनस दियो भने के हुन्छ माइनस सममा माइनस दियो भने समलाई माइनस दियो भने के हुन्छ जेमिन ड्राइभर So -3 for dimension native indexing is used to specify the dimension of summation in this -3 plus the last dimension axis 0 which is the channel dimension. What will be the resulting okay ए तीनटा ब्राकेटबाट दुईटा ब्राकेटमा गयो कसरी भयो 15 सबैलाई जोडेको हो ओके 1 4 7 ओके 1 4 7 कति हुन्छ 10 11 हुनुपर्ने 15 कसरी आउँछ हाउ alone axis 3,3/3 को साइज आउँछ कसरी आयो सता आएन त गरे फेरि तीन 5/5 को छ हैन सममा -3 गरेछ। -3 गर्दाखेरि डाइमेन्सन पो हराएको छ। यसले कसरी चाहिँ सम गरे गरेर चाहिँ एलोङ द एक्स एक्सिस गर्छ, वाइ एक्सिस गर्छ। यति एउटा चाहिँ मानौँ टेन्सर A is equal to tensor dot okay, one's column, one's size tensor and torch dot one, so get torch 1 को size भनेको म यसमा दिन्छु 3 5 ओके साइज आउँछ हाम्रो 3 को 5 को 5 को आउँछ हैन आयो आएपछि सम गरेर -3 गरिदिन्छु कति हुन्छ तीनटा तर यसको शेप चाहिँ इफ दैट सम -3 को शेप के हुन्छ 5/5 हुन्छ हैन 3 डाइमेन्सनको जोडी नि हो त 3 डाइमेन्सनमा भएको सबैको जोडी नि हो नि हैन 3 3 3 हुन्छ ओके त्यसरी नै ओके 1 डाइमेन्सन भयो 2 डाइमेन्सन भयो यहाँ डाइमेन्सन टुक्रे यहाँ डाइमेन्सन टुक्रे यहाँ डाइमेन्सन टुक्रे हैन सबै जोडेर थर्ड डाइमेन्सन के भन्छ अरे 3 डाइमेन्सनको मारेर राख्ने भनेको सबै गरेको त लघटाउनु भन्छ हैन 5 channels 5 row 5 column per channel हुँदैन -3 for dimension negative indexing is used to specify the dimension of for summation in this case -3 refers to the last dimension axis 0 okay 1 2 3 okay -3 which is the channel dimension okay channel dimension ma हैन the result will be the new tensor of size 351 this new tensor will have a same number of rows and columns as the original tensor but the channel dimension will be reduced to 1 each element in the यो रङ छ कि जसलाई यसले भनेको र यसले भनेको गरेको काम त फरक छ त किन भन्दाखेरि यसले यसको साइज निकालेको छ कतिको यसले निकालेको 5/5 को छ तर हामीले भनेको 3/5 को तर 5/5 को बनायो 1 डाइमेन्सन निकाल्दियो 1 2 3 -3 को यो निकाल्दियो त ओके इसको शेप 2 डाइमेन्सनमा पुऱ्याइदियो त 3 डाइमेन्सनबाट 2 डाइमेन्सनमा गयो त 0 1 because this got messy quickly and for the sake of efficiency that PyTorch function in some adapted from PyTorch to specialize and indexing many languages giving index names of 2 dimensions for some of such product as often in Python broadcasting or form of summarization unnamed thing is done using 3 dots but don't worry too much and about e in some because we will not use it it is the following so image gray weighted fancy is equal to cross dot in summary 3 dot cw ma c 3 dot hash w image के ये भाइ नि Oh, as we can see, there is a quite a lot of there is a lot of okay becoming okay. This is error prone, especially when the location where tensor architecture and use are far apart in our code. This has caught the eye of practitioners, and so it has been suggested that the dimension be given a name instead. Named त्यसमा एउटा मतलब पोजिसनल दिनुपर्छ त्यही भएर ब्राकेट गरिदियो भने 0.2126 0.7152 0.7722 7 else wait and maybe named tensor and all their associated FAs are the experimental features and subject to change. Please do not use them for anything important until they are released as stable okay, trigger internally. Named tensor अझै पनि ल्याएन यिनीहरूले के पाइटर्सको PyTorch नेम टेन्सर 2.3 मा automatically warning the names tensor API is prototype feature and subject to change अझै छ रहेछ न ओके नेम्स राख्न त मिल्दो रहेछ अझै पनि एक्सपेरिमेन्टलै छ आउनुहुन्छ जुन आउनुहुन्छ ओके वकारिमास्ता when you already have a tensor and want to add names but not change existing ones, we can call the method refine names on it similar to indexing the ellipsis allow you to leave out your number of dimension. यो त हेर्दैन रहेछ होला for operation with two inputs in addition to the user dimension 6 whether size of are the same of that one and can be broadcast to the other. PyTorch will now check the names for us. So far it does not automatically align dimensions, so we need to explicitly the method align as returns a tensor with missing dimension added an existing one permuted to the right order. ओके त्यसोगरी ओके नेमको कुरा त सर के छ यदि ओके यदि नाम राख्यो भने सिधै च्यानल्स भनेर लेख्न पनि पाइन्छ भन्नु खोजेको ओके tensor element type. So far we have covered the basics of how tensor, but we have not touched on what kind of numeric types we can store in tensor as we hinted in the section 3.2 using the standard Python Numeric types can be suboptimal for several reasons. Numbers in Python are objects, whereas a floating point number might require only, for instance, 32-bit to be represented on the computer. Python will convert out into a full-fledged Python object, um, a Python object with reference counting and so on. This operation called boxing is not a problem if we need to store a small number of numbers, but allocating millions get very inefficient. Listing Pythons are meant to sequential collection of objects, and there are no operation defined for say efficiently taking the dot product of two vectors or resuming or summing vectors together. Also, Python lists have no way of optimizing the layout of their contents in memory, as they are uh, indexable collection of points to Python objects of any kind, and not just numbers. Finally, Python lists are one-dimensional, and although we can create list of lists, this is again very inefficient. The Python interpreter is slow compared to optimized compiled code. Performing mathematical operation on large collection of numerical data can be much faster using optimized code written in a compiled low level language like C. Hmm. For those reasons, data science libraries rely on NumPy or introduce dedicated data structure like PyTorch tensor, which provide efficient low-level implementation of numerical data structure and related operation on them. RAM in a convenient high-level API. To enable this, the objects within a tensor must all be numbers of the same type, and the PyTorch must uh, keep track of the numeric type. Okay, so data types are here. Data type argument to tensor constructor, that is function like tensor zeros and ones specifies the numerical data type that is contained in the tensor. The type specifies the possible number of tensor can hold integers versus floating number and the number of bytes variable. The type argument is deliberately similar to the standard numpy argument of the same name. Here is the list of possible values of the type argument. Circuit torch dot float 32 torch float 32 bit floating 64 16. Okay, signed. Okay, there is okay. So on the type for every occasion. As we will see in future chapters, computation happening in neural networks are typically executed with 32 floating point precision. High precision like 64 will not buy improvements. Okay, here the higher precision like 64 will not buy improvements in the accuracy of the model and will require more memory and computing time at also. So 16-bit floating may have precision data point is not present natively in standard CPU, but it is offered on modern GPU. It is possible to switch to half precision to decrease the footprint of a neural network if needed, with a minor impact on accuracy. Okay, so it is possible to switch current seconds array. Okay, it is possible to switch to half precision to okay, but it will be minor impact on. Okay, tensor can be used as index in other tensor. In this case, PyTorch expect indexing tensors to have a 64 bit in creating a tensor with integer as argument, such as tensor torch that tensor to do will get a 64 bit integer tensor by default. As such, we will must spend most of the time dealing with float 32 and in 64. Okay. Dealing with float 32 in 64. Final prediction. It's important कुरा होइन त्यो आउँछ मलाई. Okay. Finally predicates on tensor such as point greater than 1.0 produce bool tensor indicating whether its individual element satisfies the condition. There are the numeric type in the inner cell. Managing a tensor type attribute. In order to allocate a tensor of a right numeric type, we can specify the number proper type as an argument to the constructor. For example, double points torch dot owns. So type right here torch dot double torch source unbind. Okay. So यो त थाहा छ डट डबल गऱ्यो भने ओके डट सर्ट गऱ्यो भने आउँदो रहेछ ओके टु गर्न नि मिल्छ टाइप गर्न नि मिल्छ टु गरेछ टाइप भनेर टाइपमा त सिधै यो 64 इन्टु टाइप गरेर गर्नु मिल्छ सो एपिआई टेन्सर ओके at this point we know that PyTorch tensor are and how they work under the hood. Before we wrap up, it is worth taking a look at the tensor operation that PyTorch offers. It will be of little use to list them all here. Instead, we are going to get a general feel for the API and establish a new direction on where to find these on the online documentation. Okay, PyTorch doc find the vast majority of operation on and between tensor are available in the torch module and called as the method of tensor objects. For instance, the transpose function we encountered earlier can be used from the torch module. Transpose मैले ट्युटोरियल बनाएन कि है ट्रान्सपोजको आई थिङ्क ट्रान्सपोजहरू बनाउनु पर्ला जस्तो लाग्यो ओके छुटेकाहरू 0 ले ट्रान्सपोज गर्ने भन्ने जस्तो के छ र 3/2 लाई 2/3 को बनाउनु त ट्रान्सपोज उल्टाउने नि रोलाई कोलमलाई रो 3/2 लाई 2/3 बनाउँदाखेरि ओके So there is no difference between two forms. They are used interchangeably. Okay. Creating a function for constructing a tensor like once and from. Okay, you are just indexing, slicing, joining, mutating. Function for changing the shape, stride or content of the tensor like transpose. Okay. Math ops भनेको यसमा त हेरिसकेको छ positional operation हेरिसकेको छु function for manipulating the content of the tensor reduction of function for computing aggregate values by interacting tensor like main statement यो पनि हेरिसकेको छु comparison of some function for evaluating the variable predicates over tensor like equal and max यो चाहिँ गरे हैन spectral ops function for transforming in and operating in the frequency domain like STFT and humming window यो नै हैन other operation like cross matrices like trace okay BLS and LPAC operation like basically linear algebra sort program specification was scalar vector matrix random sampling random and serialization function like saving and loading tensor यो हेर हैन यसको नि बनाउनु पर्ला ट्युटोरियल parallelism functions for controlling the number of threads for control parallel CPU execution like set num threads. Take some time to play with the general tensor API. This chapter has provided all the prerequisites to enable this kind of interactive exploration. We will also encounter several of the tensor operation as we proceed with the books starting in the next chapter. 3.7 छ हेरियो कति छ यो saving view of storage tensor metadata size offset and stride moving tensor to the GPU यो दिएको It is time for us to look a bit closer at the implementation under the hood. Values in the tensor are allocated in the contiguous chunk of memory managed by Torch. Okay, Torch dot storage instance rounds are okay. Storage is a one-dimensional array of numerical data. This is a contiguous block of memory. A contained number of given types such as float 32-bit representing a floating point number or in 64. Yeah. A PyTorch tensor instance is a view of such a storage instance that is capable of indexing into the storage using an offset and power dimension strand. Okay, multiple tensor can index the same storage as they index into the data differently. We can see an example of this figure 3.4. In fact, when we requested points 0 in section 3.2, what package tensor instance is a view of such a storage instance that is capable of indexing into storage using offset and per dimension strides. Multiple tensor can index the same storage even if they index into the data differently. We can see an example of this figure in figure 3.4. In fact, when we requested point 0 in section 3.2, what we got back is another tensor that indices the same the same storage as the point tensor, just not all of it, and with different dimensionality, one dimension versus two dimension. The underlying memory is allocated only once. However, so creating alternate tensor view of our data can be done quietly regardless of the size of the data managed by the storage instance. Okay, storage starts at 0, 2 rows, 3 columns. Two rows, three calls, tensor representation starts at 0, 3 rows, 2 calls. The number of actuals are. The underlying memory is allocated only once. However, so creating alternate tensor views of the data can be done quickly, regardless of the size of the data managed by the storage instance. Okay. Let's see how indexing into the storage works in practice with our to the points. The storage for a given tensor is accessible using a dot storage property. Points dot torch dot tensor 405321. Points dot storage via okay. Hmm. Size of 6. Even though the tensor reports itself as having 3 rows and 2 columns, the storage Another hood is a contiguous array of size 6. In this sense, the tensor just knows how to translate a pair of indices into a location into the storage. We can also index into a storage manually. For instance, point storage, point dot storage, point storage 1 4.0. Okay, storage बाट पनि instance लिन मिल्छ. Okay. We cannot index a storage about 2D tensor using two indices. The layout of storage is always one dimensional, okay, regardless of the dimensionality of any. 2D लाई 1D लाई तान्न सकिँदो रहेछ, 2D लाई चाहिँ नसकिँदो रहेछ हैन त. At this point, it shouldn't come as a surprise that changing the value of storage leads to changing the content of its referring tensor. Okay, the two गरिदियो भने okay. In addition to the operation on tensor introduced in the previous section, a small number of operations exist only as a method of the tensor object. They are recognizable after from or trailing underscore in their name, like 0, which indicates that the method operation in place by multiplying the input instead of creating a new input tensor. Okay, and returning it. For instance, the 0 method 0 out all the elements of the input. So any method without the trailing underscore leaves the score tensor unchanged and instead returns new tensor. Okay, a is equal to torch 1 3 2 गर्यो. तर यदि a is equal to 0 गरिदियो भने a सबैले 0 बनाइदिन्छ. Putting 5 star value in place of operation. Okay. Like 0 ल पछाडि underscore हाल्दियो भने सिधै गरिदिन्छ हो. Instead of creating a new input tensor and returning. Tensor metadata size, offset, and strides. In order to index into a storage, tensor rely on a few pieces of information that together with their storage unequivocally define them, size, offset, and stride. Now, how this interaction is shown in figure 3.5. The size or shape in NumPy parlay is a tuple. How many elements equals each dimension and the tensor within the storage offset is the index in the storage corresponding to the first element in the tensor. The stride is the number of elements in the storage that needs to be skipped over to obtain the next elements along each dimension. We can get a second point in the tensor by providing the corresponding index. We will have another tensor storage. Two dimension का 3/2 को बनाया था 0.0 गरेर चाहिँ point offset 2 आउँछ तपाईँ storage offset ले के गर्दो रहेछ सेकेन्ड पोइन्टको साइज गर्दाखेरि सेकेन्ड पोइन्ट गर्दा 2 आइरहेछ पोइन्टको 1 लाई लिएको 1 को 3 र 5 लिनुपर्ने हैन 0 1 point destroyed. Okay, transposing without copying. Points and बनायो त्यसो पोइन्ट्समा टेन्सर भइहाल्यो पोइन्ट्स and points to t मा points को डट टी गर्यो 3 5 डट टी मात्र ट्रान्सपोजन डट टी मात्र गर्दै हुँदो रहेछ save 3 by 2 go to transpose the T. Five, come on, 5. So stride is the job necessary to go from one element to the next one in the specified dimension dim or tuple of all stride is written when no argument is passed in. Otherwise, an integer value is returned as the stride in the particular dimension dim. 5 by 1 size go 5 by 2 size go भन्ने छ कसरी 1 को भन्छ ट्रान्सफर गरेर स्ट्राइड 1 3 को बनाएछ ओके ओके यसो 3 by यो 3 by यो कतिको साइज हो 3 ओके 3 by 1 को स्ट्राइड हो यो 2/3 को सय पो, तर स्ट्राइड कसरी लेख्दो रहेछ? स्ट्राइड लेख्यो रहेछ हो। 351 स्ट्राइड स्ट्राइड 15 बनाएर स्ट्राइड गरेर लेट आउट इन मेमोरी। ओके, मेमोरी कसरी लेट आउट हुन्छ अनि थाहा हुँदो रहेछ। फर अ मल्टी डाइमेन्सनल थिङ्स आर इट रिभिल्स द जब निडेड टु एसेस elements along each dimension. Understanding stride. Imagine a tensor as a multi-dimensional array stored contiguous in memory. The toss dot stride returns a tuple of integers where each element represents the stride for a specific dimension. The stride value indicates how many elements you need to skip in memory to get move to the next element in the dimension. Okay. 5वटा पछि एउटा जम्प गर्ने, 5वटा एउटा जम्प गर्ने, त्यो The tensor has a shape of 351 मा रिअरेन्ज गरेको थियो। ओके, 3 तीनटामा 5 को भित्र 1 मात्र हुने। ओके, यो पनि बुझेँ ल। The stride is 5 1 1. Looking at the stride 0 is 5. So stride for the first dimension channel to move to the next element in the channel dimension. That is from the first element to the second element in the first row. Okay, we need to skip 5 elements in memory because each row has 5 elements. तो बुझे 5 तो बुझे। ओके, तीनटा छ पहिला। पन्ध्रको भागलाई कसरी डिभाइड गरेको छ? यसरी तीनटा गरेछ हैन? तीनटा रो गरे हो, 5 वटा। जिरो गर्दै यहाँ 1400 पुगेको छ हैन? यसले भन्छ के भन्दाखेरि so the stride for the first dimension channel. Okay, to move the next element in the channel dimension, that is from the first element to the second element in the first row. First element to the second element row, we need to skip 5 elements in memory because it has 5 elements. Okay, stride 1 is 1. Stride for second dimensional row, moving to the next element to row requires skipping only one element since element in the row are stored continuously. Okay, all our stride values YouTube मा हेर्नु पर्ला अहिले stride Okay, keep all my Instagrams. Mm. Transfers transposing in higher dimension 3 4 5 को डाइमेन्सन गर्दाखेरि 3 4 5 को भन्यो ट्रान्सपोज गर्दा 5 4 3 को भन्छ ओके सम स्ट्राइड गर्दा नि 20 वटा ओके सम टी भनेको पहिला 3टा रोमा छ 3टा रोमा छ ओके 3टा सेक्सन 3टा एउटा दुईटा तीनटा हैन त्यसैले एउटामा 4 वटा 4 वटा 4 वटा 4 वटा अनि एउटा 5 वटा 5 वटा 5 वटा ओके सो यसको 500 को 20 वटा 20 वटा हुन्छ अरे ओके 20 त्यसैले 5 वटा अरे नेक्स्ट बजारलाई 4 वटा हुन्छ नि त A tensor whose values are laid out in the storage starting from the rightmost dimension onward is continuous. Continuous tensors are convenient because we can visit them efficiently in order without jumping around in the storage. Improving data locality improves performance because of the way memory access works on modern CPU. This is advantage, of course, depends on the way algorithm visits. Okay, continuous tensor. False is continuous. Some answer type in PyTorch only work on continuous tensors such as view, which we will encounter in the next chapter. In that case, PyTorch will all throw an internal relaxation and requires us to call a continuous explicitly. It's worth noting that calling contiguous will do nothing and will not hurt performance if the tensor is already continuous. If the case point is continuous, while the tensor is not, the point is continuous. So it's continuous false. We can obtain a new continuous tensor from a non-continuous using the continuous form method. Okay. Point गरेर यदि हामीलाई यसलाई चाहिँ के बनायो ट्रान्सपोज गराउँदाखेरि बनायो स्टोरेज छ ओके point that stride गर्यो ओके सो point continuousलाई point ले continuous गर्दैन point continuous हुँदो रहेछ ओके ओके स्ट्राइड 3 1 को 1 2 को थियो अब 3 1 को भने ओके सेभ 3/3 को रोज कलम्स मुभिङ टेन्सर टु द जीपीयू यो त थाहा छ हौ important. So far in this chapter, when we have talked about storage, we have means memory on the CPU. PyTorch tensor also can be stored on a different kind of processor. Graphics processing unit CPU. Average PyTorch tensor can be transferred to one of the GPUs in order to perform massively parallel fast computation. All operations that will be performed on the tensor will be carried out using CPU specific routines that comes with PyTorch. So as mid 2019, the main PyTorch release only have acceleration on GPU that have support for CUDA. So PyTorch can run on AMD, okay, ROC, and the master repository provides support, but so far you need to compile it yourself. Before the regular build process, you need to त्यही भएर त्यत्तिकै महँगो छ क्या एएमडी एएमडी ग्राफिक्स किन महँगो हुनु रिसर्चरहरूलाई कामै छैन support for Google Tensor TPU is a work in progress. Okay, with the current proof of concept available in public Google Colab, implementation of data structure kernels on other GPU technologies such as OpenCL are not planned at the time of this writing. Okay. Managing a tensor device attribute 2.9.3.9.1 while moving. Okay, moving tensor also. Okay. In addition to the type, PyTorch tensor also has a notion of device, which is where on the computer the tensor data is placed. Here is how we can create a tensor on the GPU by specifying corresponding. Okay, यो त टर्च गर्दाखेरि सिधै टाइप डिभाइसको कुरा लेख्ने यदि भएन भने डिभाइस इज इक्वल टु इफ कुडा डट इज एभाइलेबल भन्ने मेथड कल गर्न सकिन्छ. ओके, doing so return a new tensor that has the same numerical data but stored in the RAM of the GPU rather than in the regular sorry note that the data is locally stored on the GPU. We will start to see the speed ups mentioned earlier when performing a mathematical operation on the tensor. In almost all cases, CPU and GPU based tensor expose the same interface user facing API, making it much more easier to write code that is agnostic to where exactly and the happy number crunching is running. If our machine has more than one GPU, we can also decide on which GPU we allocate the tensor by passing a zero-based integer magnifying the GPU on the machine, such as okay, कुडाको 0 मा कुडाको 1 मा गर्न मिल्छ. Note that the point GPU tensor is not brought back to the CPU once the result has been computed. Here is happens in the line. So point tensor is copied to the GPU. The new tensor is allocated on the GPU and used to store the results of the multiplication. A handle to the GPU tensor is returned. Therefore, if we want to also add a constant to the result, the addition is still performed on the GPU and no information flows to the CPU unless we print or access the resulting tensor. In order to move the tensor back to the CPU, we need to provide a CPU argument to the to method. Okay, to device CPU. Okay, and we can also shorthand the CPU and CUDA instead to method like to okay point dot CUDA point dot CPU. Okay, numpy interrupt. Okay. I mentioned numpy here and there while we do not consider numpy requisite for reading this book. We strongly encourage you to become familiar with numpy due to ability in the Python science system. PyTorch tensor can be converted to numpy arrays and vice versa very efficiently. By doing so, we can take advantage of the huge swath of functionality in our wider Python ecosystem that has built up around the numpy array type. This zero copy interoperability with Python, again numpy arrays is due to the storage system working with the Python buffer protocol. So from numpy गर्न सकिन्छ छ. So the return array is the same underlying buffer with the tensor storage. This means the numpy method can be effectively executed at the basically no cost as long as data sits in CPU RAM. It also means modifying a numpy array will lead to change in the originating tensor. This tensor is allocated on the GPU. PyTorch will make a copy of the content on the tensor into the numpy array allocating on the CPU. Generalized tensors are tensors too. General tensors are multi-dimensional arrays, just as we have seen in this if we reach a peek under the hood of the PyTorch, there is a trace how the data is stored under the hood is separate from tensor API as discussed in section 3.6. Any implementation that uses a contract of the API can be considered a tensor. PyTorch will cause the right completion function to be called regardless of whether our tensor is on the CPU or the GPU. This is accomplished through a dispatching mechanism, and that mechanism can cater to other tensor types by hooking of the user facing API to the right backend functions. Sure enough, there are other kind of tensor. Some are specific to certain classes of hardware like Google TPUs, okay, and other have data representation that offer from the dense array style we have seen so far. For example, sparse tensor you store only non-zero entries along with index information. The PyTorch dispatcher on the left in the figure 3.8 is designed to be extensible. Extensible. What is extensible? Okay, extensible. The subsequent switching done to limit the various numeric values of figure 3.8 shown on the right is a fixed figure information accorded into its backend. So we will meet quantize tensor in chapter 15, which are implemented as another type of tensor with a special computation backend. Sometimes the usual tensor we use are called dense or strided. We differentiate them from tensor using other memory layout. So torch dot add a bigger a dot device a dot logout a dot btype dispatcher a dot dense each dense CPU is CUDA is disperse is quantified, okay, dispatcher, okay, add CPU. Yes, with many things the number of kind of tensor has known as PyTorch supports a broader range of hardware and application. We can expect new kind of continue to rise as people explore new ways to express and perform computation with PyTorch. So serializing tensor, I guess save and load the new, okay, creating a tensor on the fly is all well and good, but if the data inside is valuable, we need to want to save it. The file and load it back at the same time. After all, we need to want to have a written model from scratch every time we start running our program. PyTorch uses pickle under the hood to serialize the tensor object, plus dedicated is serialization code for serialization code for the storage. Here is how you can save our points tensor to an output a file. So torch dot save here points, okay, तो points लाई नाम दिन सकिँदो रहेछ, डट्टी गरेर पिकल बनाउँदो रहेछ होइन. As an alternative, we can pass a file descriptor in a line view of the file name, okay, with open as starts.save point f, okay. Loading our model back into similarly one line or okay dots load गरेर सिधै लोड गर्न मिल्दो रहेछ. अर्ग्युमेन्टले with open गर्न मिल्दो रहेछ होइन. with open dot rb read sf point dots load f गर्न मिल्दो रहेछ. okay, same. While we can quickly save tensor this way, we only want to load them with PyTorch. The file format itself is not interoperable. We can read the tensor with software other than PyTorch depending on the use type. This may or may not be a limitation, but we should learn how to save tensor interoperably for those times when it is. We'll look next to how to do it. Okay, serializing to SD5 to S5 by every use case is unique, but we suspect needing to save tensor interoperably will be more common when introducing PyTorch into existing systems that already rely on different libraries. New projects probably won't need to do it as often. For those cases, you need to, however, you can use the SDF5 format and library. Okay, SDF5 is a portable, widely supported format for representing serialized multidimensional arrays organized in a nested key value dictionary. Python support HDF5 through the H5 py library, which is the returning data in the form of numpy arrays. So 5 to create data numpy closer here codes. Here code is a key. The key into the we can have other key even nested ones. 5 तो माथिको राइटको लागि यो राइटको लागि w भन्छ राइटको लागि भयो यो r भनेको रेडको लागि so this set is equal to f codes last points is equal to this domains to okay this let's see going to this fact we can pass forward return object to the path no by okay टेन्सन बनाउन त्यो गर्न सकिन्छ अनि यहाँ गर्न सकिन्छ नि कुरो once we have finished loading data we close the file. Closing the file invalidates the dataset and trying to access as long as we stick to the other zone here we are fine and we can now work with the last point tensor. Conclusion: now we have covered everything we need to get started with representing everything in floats. We will cover other aspects of tensor such as creating views of tensor, indexing tensor with other tensor, and broadcasting which simplifies performing element-wise operation between tensor of different size or shapes as needed along the way. In chapter 4 we will learn how to represent real-world data in PyTorch. We will start with simple tabular data and move on to something more elaborate. In the process we will get to know more about tensor. Exercise there in the summary has neural networks transform floating point representation other floating point representation. The starting and the ending are typically human interpretable, but the intermediate representations are less so. These floating points representation are stored in tensor. Okay, tensor are multi-dimensional arrays. They are the basic data structure in PyTorch. PyTorch has a comprehensive standard library for tensor creation, manipulation, and mathematical operation. Tensor can be serialized to disk and loaded back. All tensor operation in PyTorch can execute in the CPU as well as GPU with no change in the code. PyTorch uses the trailing underscore to indicate that the function operates in place on a tensor. Okay. So chapter 4 हामी अब चाहिँ I think भोलि पढ्छु म आज पढ्न सक्दैन